Okay, here is our second module on the, as portrayed on the physics CXC learning. Well, as portrayed in textbooks. I couldn't find the good words. Sorry. So let's try this now. We're going to be doing forces at rest. So this is the next topic. And we have 20 questions. So just a while ago we had 22. And now we have 20 questions. I'm going to start. I think I'm going to write in red. Yeah. Red would be nice. Good. Okay, so the force, the unit of force is, this is the, Pascal is the unit of pressure. J is the unit of energy, so that's not it. B is the unit of force. This is newtons. Right. There's B. And this one is the unit for velocity or speed. An example of a second class lever is, it's not a tweezer, it's not a crowbar. Tweezer is a third class. A crowbar is a first class. Sugar tongs, third class. It's a wheelbarrow. Let's remember that. First class levers, you would have the load, then the fulcrum, and then the effort. That's first class. Second, you would have the fulcrum, the load, and then the effort in this order. And then you will have third class levers, which you have the fulcrum, the effort, and the load. And how I remember this is by saying life, free, and fell. Life, free, and fell. So life is the first class lever. Okay, like the crowbar. We have the load, remember a crowbar. Suppose you were lifting up something, you would have the load right here. And then this would be the fulcrum right here for the lever to turn on. And this would be the effort, right? So let's say you're opening a lid, right? A lid, what do you call those? Like the manholes? Yeah, suppose you're lifting up one of those. So this would be the load, the fulcrum, and then this would be the effort right here. And then now let's say we have a wheelbarrow, which is the second class lever. A wheelbarrow, right? You have the wheel. You have the wheel right here. I can't even draw it here. And you have something like that, and you have this thing. So you have the fulcrum right here where it's gonna turn. So the fulcrum is here on the wheel, F. And then you have like maybe some dirt in here. So this will be the load. So you notice FL, and then the hand here would be the effort. FLE. See how that works? And then for tweezers or sugar tongs, let's turn it this way. Tweezers and sugar tongs work with the same basic concept. You have the fulcrum right here, where it gets squeezed. And then you have the effort being applied right here to squeeze it. And then you have some load that's being picked up. So sugar tongue and tweezers, same idea. F-E-L. Good? Alright, so I hope that explains that. Now the length of the plank is, so here we have the item below refers to questions 3, 4, 5, and 6. And we have, let's look at this, it looks nice, it looks like a turning moment question. And it says the length of the plank is, so the length here, the distance between the pivot, sorry, the distance between the pivot and this over here is 2 meters. And the distance here to the other end here is 8 meters. So you add these two and you get 10. So that wasn't so hard. That was a giveaway question. Then it says the center of gravity acts at the dash meter mark of the plank. Center of gravity always acts at the center of whatever object we're talking about. And if this is 10 meters long, it would act at the 5 meter mark. So the answer is C. What is the weight of the plank? Now, the weight of the plank will be at the 5 centimeter mark. So to get from 2 to 5, we have to add 3. So let's say that 3 was here somewhere. And so this will be 3 meters right here, and we want to find x. Now, the weight of the plank, if this is balanced, we're assuming that this is balanced, we're going to say that anti-clockwise moments equal to clockwise moments. Let's go down a little bit. So anti-clockwise moments equal to clockwise moments, assuming you already learned this from my read-alongs or from class, we're going to work it out. So anti-clockwise moments will move in this direction, opposite to the way a clock, the hands of a clock would move, right? And clockwise would be this way. So this is anti-clockwise, and this is clockwise. So we know that anti-clockwise moments equal to clockwise moments. And that is just saying that force times distance on the anti-clockwise side is also equal to force times distance on the clockwise side. And so they will balance out. So the force here is 30 newtons. And the distance that the force is away from the pivot is 2 meters. And the distance, let's go, so we're looking for force here, that's keeping it balanced. And we have a distance of 3 meters. Now this will give us 60 Newton meters, and then we want to solve. So basically, if it's balanced, whatever anti-clockwise moment or whatever the moment is equal to here should be equal to the moment over here. So this is 60 newtons on the anti-clockwise side. You could already figure out what can make this here 60. So if you have 3 meters, what do you have to multiply by 3 meters to make it to be 60? Right, that will give you 20. So we divide both sides by 3 meters. Cancel, cancel, cancel these two. You end up getting 20 newtons. Okay? So that'll be your answer, because 3 times 20 gives you 60, just like 30 times 2 will give you 60. So that will make it balanced. If the weight of the plank is 10 newtons, then it will tilt. Will it tilt anti-clockwise? Will it tilt clockwise? Will it balance, or will it break? Now, if it's less, if the clockwise side, because we're saying the weight is on the clockwise side, right? So if the weight is 10, then this will give us only 30 and not 60. So therefore this side will be heavier than this side, and so it would therefore tilt anti-clockwise. So there's a lot of thinking going into that. The unit of energy is, this is the unit for pressure, this is the unit for force, and this is the unit for velocity or speed. So energy is joules. Which of the following sources of energy is non-renewable? This is renewable. This is renewable. That's renewable. Nuclear is not. Okay, moving up. The item below refers to question 9. And look at it. We have deuterium and tritium fusion. Then we have helium coming off, a neutron, and some energy. This is an example of what goes on in nuclear reactors, in car engines, in a cell, or in the sun. No, this is not in A or C or B. This doesn't happen on Earth. It requires way too much energy to happen. So from that, then it happens on the sun, in the sun. The conservation of energy states that energy can be created but not destroyed. That's totally wrong. Energy can be created but destroyed. Energy can be created but destroyed. Okay, no. Energy cannot be created or destroyed, but can be transferred. So C is correct. Energy cannot be created or destroyed. However, it can be transferred. If a mass of 10 kilograms is lifted through 2 meters, how much work is done? work is equal to force times distance. And if you have a mass of 10 kilograms, you can also, work is equal to mgd. So basically, you can change this mass into a force by multiplying it by 10 newtons per kilogram. That cancels. And then you multiply the distance, which is 2 meters. And that will give us 200. So let's see, we have, oh, so yes, so my bad. These should have negative ones up here. So this would have been a free question for the kids. But the answer is 200 newtons per meters, right? What is the speed of a 2 kilogram mass coconut falling to the ground from 10 meters? So we have mass, 2 kilograms. We have height, 10 meters. We have gravity, 10 newtons per kilogram. So we have mass, height, and gravity. MGH. We're looking for velocity. So note well that the potential energy something has will eventually be the kinetic energy it will require. Right? So we could say MGH will be equal to the mass of the same thing times the velocity squared over 2. If we're solving for velocity, we know the mass is going to cancel out simply because we're using the same mass. We're looking for the same object. The same object that has the stored energy is the same object that will be falling. So if we transpose on both sides, we end up canceling mass. So we end up with GH equals to V squared over 2. And if we transpose it 2 on both sides, we end up with 2GH. Then we could solve for velocity by getting rid of this, by multiplying this by a half up here and multiplying this whole thing by a half, which will give us V equals to the square root of 2GH. And then we could just fill it in. So in filling in, we said V is equal to the square root of 2 times 10 newtons per kilogram times the height. And the height was 10 meters. Right? And right, so we should get 2 times 100. Is it there? Oh boy. It is not there. I did not put the correct one. It's supposed to be D, by the way. It's supposed to be D. It's supposed to get, let me see. That was root 2 times gravity times height. Yep. And you should get 200 in here. Right, and from there you will get 14.1. So this would have been it without that 5, right? So 14.1. My bad. This is what when you're trying to trick children. So could you imagine 11 and 12 would have been crossed off, right? But the answer is 14.1 meters per second. And it should have been D. Alright, a plane B220 is fully loaded with a mass of 600,000 kilograms. It can travel to a height of 15 kilometers with a speed of 200 meters. What is the gravitational potential energy? Okay, so we have mass, the mass, which is 600,000 kg. We have height, which is 15 kilometers and must be converted to meters, which is 15,000 meters. And then we have speed. We have this speed, which is 200 meters per second. And you have gravity, which is 10 meters per second squared. So you could interchange it. And well, if EP is equal to mgh, we're just looking at this, this, and this. So we just multiply 600,000 times 10 times 15,000, and that will give us 9 to the 10th, 9 times 10 to the 10th power. And of course I have the correct units this time. Wow, yay! Alright. Yes. Sometimes it happens that, so in a case like this, I will just map the test out to 18. I'll just give the 2 points and get the children smiling. No biggie. Now, energy in a battery operated radio is transformed in the following sequence. So if you have a battery, you're going to start off with chemical energy, and then it's going to travel through the wires, so we have electrical energy, and then we're going to have sound. So in nuclear power stations, large atoms are split into smaller atoms. This process is referred to as nuclear fusion, no. Nuclear fixation, no. Nuclear fission, yes. Nuclear fissures, no. What is the power? What is the unit of power? As watts. How much work is done when a mass of 10 kilograms is lifted vertically through 10 meters? Gravity there. So this is work equal to force times distance, and we just convert the mass into a force, which is the weight. We're multiplying here and then we have the distance, which is 10 meters. So I have 3 zeros right here, so the answer would be 1,000 newtons per meter. See? Oh, I know what happened. I was trying to fix one and I messed it up. Right? Yeah, that's what happened. No. Oh, so this is correct. This is correct. So this, oh my bad. Oh my bad. You can, so this is indeed correct. So we could keep this. Did I have anything else here? Speed, that was fine. Just didn't do the upper. And then I could fix them, I'm gonna fix them right after, so that you would be fine. With this one, I would have had to remove these because the answer is actually 1,000 Newton meters. Sometimes you make these silly mistakes. It's okay. Okay, so that would be 1,000. And then we have now, which of the following is not a type of pulley? Block and step in, single fix, block and tackle, single moving. Block and step in. Nope, never heard of that one. Now all of the following are simple machines except you have the wedge, that's simple. The lever is simple. The screw is simple. The bicycle is a complex machine. It's a bunch of simple machines put together. Which of the following situations would have the lowest center of gravity? You gotta use the imagination now. So, a tall three-legged stool, balancing a fat sharp pencil on its point. This goes out one time. A ballerina on point using one leg. A stout, broad teacup. So remember, the lower center of gravity things gotta be short, and they also need to be broad. So this one has the best orientation to say that it would have the lowest center of gravity. For piece of wind blow, this will be the least likely to fall or topple. Alright, so this is the end. I'm gonna fix up this, clean it up. But before I do, I'm gonna write down all the answers here on the side. So if you are writing your answers down, you could look back and see what it is. So 1 is A, 2 is C, 3 is A, 4 C, 5 B, 6 A, 7 C, 8 C, 9 D, 10 C, 11 B, 12 D, 13 A, 14 C, 15 C, 16 A, 17 D, 18 A, 19 D, and 20 D. So I hope that you were able to get at least 20 out of 20 despite me not having the right things here, which I'm gonna fix right now. I'm closing tools for a minute. And so these were correct. These needed to be put up somehow. If you want this test, just email me. I will send it to you. I'll put my email in the description box. And I'm going to put this as the correct answer. So I'm going to put this as 14. What was it again? 14? Let's just put 14 because there's 14.4 I think. Let's see. Let me make sure. 14.1. Alright. So I'll just leave it as 14. And then these would have needed to move right here. Right. Okay, so now it is on track. Right on track. Alright, so I hope this helps you around for our next virtual learning CXC style multiple choice questions. And do send me any comments to help me out or to help yourself out and tell me what you'd like to see next. Alright, adios.